Greetings, everyone. Let's go further into vector calculus. We're going to talk about a way of generalizing the definite integral from Calc 1. It's called a line integral or a path integral. Okay, often line integral, but the name line sort of gives you the wrong impression that we're always going to be using lines, when very often we're not. Most of the time we're not using lines. We'll start there though. So a line integral is taking the idea of a one-dimensional integral but applying it to something other than an axis. Okay, so imagine being able to sum a continuous function, okay, over some subset of your domain. In other words, a path cut out of your domain. So if you have a two-dimensional, the xy plane is your whole domain. Imagine drawing just some curve in that domain and being able to just integrate while walking on that path, okay, instead of having to integrate the entire domain. Okay, so imagine something like this. You've got a function, okay? You've got some surface, which is a fxy, right, a two-variable function. It's a surface. But out of the xy plane, I'm only going to cut along this path. In other words, I'm just going to take points along this curve. And then each one of those points has a function value. And I'm summing up all of the function values along that curve. That's what a line integral basically is. Now, of course, it doesn't have to be exactly like this, and it doesn't have to always be thought of as z-values, but that's the closest thing to your original integral, so that you can make this next leap forward, okay? It actually has a much bigger application than that. So typically, this is the way we write a path integral. You will have your function, whether two-variable or three-variable. For our cases, we're just doing those two different types. And for your integral boundaries, instead of putting numbers, the curve C is considered the boundary. So you put that there, okay? And then notice the differential portion is not x or y or t, it's s. We're actually using infinitesimal little pieces of arc length all the way along. There's a little piece of arc length here, little piece of arc length there, little piece of arc length there. If you think about it, that's actually what you're doing with your original integral all the way back from Calc 1, right? You're taking little bitty slices of the x-axis and calling them dx. That's essentially what I'm doing here, but instead of an axis, I'm twisting it up into a little curve, and I'm taking little small pieces of its length. ds, little small pieces of arc length, or just curve length, not arc length. Okay, so that's what this is. This is just a more generic version of your definite integral. Okay, and it's either two-variable or three-variable functions. When you're doing this of a two-variable function, this is how you can visualize it. You know, your two-variable function is some surface, but I'm only following some path. We don't really have good ways of visualizing f of three variables, right? We can take little individual slices of them, level curves, if you will, level surfaces, if you will, right, of those kind of functions. But to graph the whole thing is, very extremely difficult to even imagine. But you can see how the idea would apply still. I am integrating some function over some path that's cut out of its domain. In this case, the domain would be the entire space, x, y, and z axes, right? And I'm just going to pick some space curve and just add up the function all along those points, okay? So, some quick thing to notice. If your function is just 1, right, a constant function of 1 times ds, then what are you doing? You're just doing an integral along a curve of its length, right, of little pieces of its length. What happens is you'll just get the length of c, right, length of the curve, if you do this integral. So what is that the same as, right? It's the same as the integral from A to B of, if it's in parametric form, right, the derivative pieces squared dt. So you can equate something like this with something like this. In other words, I can take something that's in a curve length format and then generalize it back into just a normal definite integral as long as I can parameterize it. Okay, so let's generalize that idea a little bit. Parametric form of one of these line integrals basically becomes a definite integral. So it brings it back into the home space that you're accustomed to, right? So your line integral here, okay, then gets reparameterized, x and y get substituted for some function of t. Well, where do those come from? From the curve. Whatever curve I'm following, I can write a parametric equation for, right? So whatever c is, I write some sort of vector function, parametric form, and then those parametric pieces are what I plug in for x and y. Also, and a small piece of curve length is just the square root of the derivative pieces squared and summed, right? Where do those come from? Again, from here, right? Take your derivatives, square them, and you get your arc length piece, okay? All right, so I can convert any one of these integrals into something with a parametric, and it makes it more recognizable as a plain old definite integral when you do that, okay? Here's a little quick link for you. If you allow your curve to just be the x-axis, should start sounding familiar here. We usually integrate one-dimensional integrals over the x-axis, right? That's how you start out in Calc 1. We integrate on the x-axis. Well, the parametric form for the x-axis is just x and 0, right? 0 in the y is just going left and right on the x. Well, if I plug that in, right, put x in for x, put 0 in for y, then basically I've just got a function of x, whatever it happens to be. It's just some function of x. And then the length, the derivative of x is 1, the derivative of 0 is 0, 1 plus 0 is 1, square root of 1 is 1, and then derivative, differential piece of whatever that length is, so dx. What does this become? Basically just your plain old definite integral from Calc 1. Okay? So a line integral is just the more generic version of the definite integral from earlier calculus. Okay? But we get to move around in all of the different directions of space, and we get to follow whatever path we choose or deem necessary. First example, let's integrate along a curve in between the points 1, 1 and 3, 5, okay, out of the xy plane, and I'm going to integrate the function 2 times x squared minus y, okay? Now 2 times x squared minus y is a parabolic cylinder, basically, where it's just moving sideways along the y-axis there. And I'm going to use, in this first one right here, a line to go between the 2 points in the domain. And then I'm going to do it again, but this time I'm going to use a parabola where 1, 1 is the vertex, and it goes to 3, 5. So the point here is it's the same 2 points, but it's a different path. So it's actually a different set of points we're integrating over. And you're going to see that even though it's the same beginning and ending point, and it's the same function, we're actually going to get different values for this one. Sometimes you might get the same value, but these two are going to be different. Okay, so let's take a look. I want to convert this into parametric form, which means I need some sort of parametric setup from my curve, right? So if it's a line just between those 2 points, it's easy enough to see that my curve just needs to be something with 2 linear relationships of t. I'm starting at 1, and I'm going to add 2, y is starting at 1, and I'm going to add 4. And then I'll just be integrating between t equals 0 and t equals 1, right? Because at 0, I'll have the 1 point, and at t equals 1, I'll have 3, 5. Okay? So there's my parametric setup. Let's go ahead and put everything into the integral and get it ready to go. This is going to be equal to the integral from 0 to 1, because those are my two t values for my limiting pieces of the curve there. I've got my 2 times x is 1 plus 2t, right? This is my x right here. And this is my y right here. Okay, so 1 plus 2t squared minus y, 1 plus 4t, and then ds. So I've got to do the length of the derivative here. What is c prime, right? Don't forget to remind yourself what c prime is right here. Or r prime if you're calling it r, whatever. C prime is going to be the vector 2, 4. Right? The whole time. So it's a constant tangent vector there. So then times the square root of 2 squared plus 4 squared, since those are my x and y derivative pieces, dt. Right? So this line integral, this path integral, then becomes this parametric definite integral just by plugging in the parametrics for x and y. And I can just simplify from here. Square root of 4 plus 16 is the square root of 20, right? Which is 2 square root of 5 times the 2 that's already out here. So I have 4 square root of 5 out front, integral from 0 to 1. Let's go ahead and multiply this out. That's going to give me 1 plus 4t plus 4t squared, and then minus 1 minus 4t. And dt is still there. Well, this is nice. Plus 1 minus 1 plus 4t minus 4t. So all I'm really integrating is this guy right here. Okay. So I'm left with 4 square root of 5 times 4 thirds t cubed evaluated from 0 to 1. When I plug in 0, I get 0. When I plug in 1, 1 cubed is 1 times 4 thirds. So I get 4 thirds times 4 square root of 5. So that's 16 square root of 5 thirds. Okay? Now what did we just find here, right? We took a path in the xy plane, right? And then we were summing up all of the z values that just go above that particular path. Not the whole plane, not the whole surface. Like a little sliver of the surface there, right? All of the z values underneath just that path leading up to that. Okay, so same idea. I want to do a path integral here, but the path is slightly different. Even though it's the same function, same points, the path is slightly different. Let's look at that path for a second. It's going to be this parabola where the beginning point, the vertex, is 1, 1, and it goes to 3, 5. So that's this standard rectangular equation. Let's go ahead and convert that into a parametric equation. Okay, so if I let t be this piece right here, right? Let t be that piece. Then I've got y equals t squared plus 1, and I've got x equals t plus 1, right? Because t is x minus 1. So I can easily get my curve here. Let's make some space. My curve is going to be the parametric where x is t plus 1 and y is t squared plus 1. Okay, so let's double check. Does it go through the points as expected? When t is 0, I get 1, 1. Okay? And when t is 1, I get 2, 2. Okay. When t is 2, I get 3, 5. There it is. So from 0 to 2 on my t. Okay? That does mean when I'm converting to parametric, I'm going to be doing an integral now. I'll go ahead and bring the 2 out. From 0 to 2, because those are the t values that started and stopped. Okay? Little side note, don't forget, once we step into a parametric world like that, we've actually oriented the integral, right? Before, we haven't. It's just over a curve, okay? But once we put it into this parametric form, it's got to start somewhere and end somewhere because we're actually assigning values of t, a beginning and an ending value of t. So it's going to have that orientation, which is why I have the arrows drawn on there, okay? All right, so let's plug in my x. That's going to be t plus 1 squared minus my y, t squared plus 1. And then that's times ds. So I have the square root of, and then a dt here, right? Let's go ahead and do our c prime so we can do that. C prime is 1 and 2t. All right. That means I have 1 squared plus 2t squared, right? Okay. Let's simplify out here. I've got t squared plus 2t plus 1 minus t squared minus 1. Oh, look, it worked out again like last time, right? My t squareds are going to add to 0. My 1s are going to add to 0. That's nice. So I'm left with a 2t here times the square root of 1 plus 4t squared dt. All right. Well, it looks like we're setting up for a substitution here, right? The derivative of the inside piece is going to be 8t. And right now I've got a 4t. So I'm going to need to balance out a little bit here. I'll put a 1/2 out front. From 0 to 2, I have 8t at that point, right? Because 1/2 times 8 is 4. Square root of 1 plus 4t squared dt. That one's ready for substitution, right? Your substitution there would be letting u equal to 1 plus 4t squared. So my du would be the 8t dt. And of course, that's going to be the square root of u. And when I integrate that, I'm going to get to the 3/2 power. Okay? So I've still got my 1/2 out here from here. And then I've got 2/3 from dividing by the new power. 1 plus 4t squared to the 3/2. And then that's being evaluated from 0 to 2. All right. So I can immediately wipe out these 2's. And that's going to leave me with a 1/3 times. When I plug in the 2, I get 4 times 4 is 16, plus 1 is 17 to the 3/2. Minus, when I plug in 0, I've got 1 to the 3/2, which is just 1. And I guess the only, you could simplify that a little bit. That's going to be 1/3 times 17 square root of 17 minus 1. That's about all you can do. Okay? Now let's take a real quick look at punching in the actual values of these so we can compare them. The one on the left over here is around 11.93. And this guy right here is around 23.03. Okay? So as I was telling you, we got different values, even though it's the same function, right, on the same beginning and ending points, but it's a different path, okay? Now, some functions, some integrals that we do, if they have the same beginning and ending points, it'll always give you the same, okay? We have a special category for those. We'll talk about it in the next section. But in general, it's not guaranteed, as you can see, just because I have the same beginning and ending boundaries, right? The curve itself is important. The fact that I'm integrating along a certain path does actually matter, okay? Okay, so just a quick look at what we were just doing there with those two integrals. Here's our domain, the whole xy plane for that function f. And remember, we picked the 2 points in there, like a start and a beginning, the 1, 1 and the 3, 5 there. So what I've also got for you to see now, those are in the domain. Here's the actual function, right? There's the parabolic cylinder we were looking at before, right? Absolutely. Okay, so take a look at where those dots are in relation to the function. They're underneath this side, right? So if I'm going to pick a path between the two, for example, the straight line path between those two, and then if I were to integrate, notice it would hit the surface like that from underneath. It actually follows the surface from underneath there like that. And then the integration would be like putting all this together. It would be like taking all of these y values right here that you see, all of those right here, and just adding them all up to get this little sheet like this. So that first line integral with the straight line is really just doing that for us for right now. Okay, but we also had curve number 2, right? Parabola going between the two in the domain, right? Notice it is physically in the domain, right? That's a domain curve. Okay, now here's my surface, and if I integrate that one, right, it peels off onto the surface like that, which you can already tell that that's different than the other one. It's coming out wider, so it's going to get some of the higher up z values there. And look, there it is. This is the second line integral. If someone actually were to grab a line integral underneath this thing. Continuing more with that same kind of a function example here, I want to show you how our curves can be what we call piecewise smooth. And what that means is that you can have a path that's actually different curves attached end to end. They don't necessarily have to be smooth or differentiable paths at a place where they meet, but as long as they're piecewise smooth and then they meet end to end, you can actually count it all as one path, and the integral will still be performable, right? Still be doable. Here's an example of that right here. I'm saying that my curve, this time C, is actually the sum of 2 other curves, but it's still between the points 1, 1 and 3, 5. Okay? But it's the 2 perpendicular lines where it goes from 1, 1 to 3, 1, and then from 3, 1 to 3, 5. Okay? So on your 3D grid here, it's still that same parabolic cylinder, but it'll look like this weird hook, right corner hook thing looking piece of the surface there that will be integrating all of those particular z values. All right. So what I have to do then is I have to split this into 2 separate integrals, because I'm going to have 2 separate parametric parameters. C1 is going to be the parametric that just goes from here to here in a straight line. So that's going to be the 1 plus 2t we saw before, but y stays constant at 1 the whole time. And then C2 is going to be where x stays constant at 3 the whole time, and y then changes the 1 plus 4t like that, right? So each one of these curves in its own right has technically a separate t value, okay? Where I'm letting t be 0 to 1 here, and then I'm letting technically a brand new t be 0 to 1 here as well. It's two separate parameters, even though I'm using the same letter, okay? So I'm going to have to actually set up two separate integrals here. I'm going to be integrating C1 right here. To set that up, I plug in the 1 plus 2t. It's going from 0 to 1. I have 1 plus 2t quantity squared minus the y value of 1. Okay. And then I need the differential length piece, right? The ds. So what's C1 prime here? That's going to be 2, 0. Right? While I'm at it, let's go ahead and get C2 prime. That's going to be 0, 4. Well, what's the square root of 2 squared plus 0 squared, right? It's going to end up being that 2 value again, right? So times 2, and then I've got dt. Plus the C2 integral now. So again, that's going to go from 0 to 1. This 2 comes from the function still. 0 to 1, technically I'm starting over with the other t parameter, X squared is 3 squared minus y, so minus 1 minus 4t. And then the length is going to be 4 again, because I've got 0 squared, 4 squared, square rooted. The length's going to be 4 dt like that. Okay? So there's my C2 integral, and there's my C1 integral. And now I just have to perform both of them and simplify, right? Okay? So I've got my 4 here for this one. Integral 0 to 1. 1 plus 2t squared is 1 plus 4t plus 4t squared, but then I've got minus 1 also. So those are gone. dt. Over here, I've got an 8 out front. 0 to 1. That's 9 minus 1 is 8 minus 4t dt. All right. So let's see here. 4 times, I'm going to have 2t squared, and I'm going to have plus 4 over 3t cubed, and that's from 0 to 1, plus 8 times 8t minus 2t squared, and that's going to be evaluated from 0 to 1. Okay. Both of these instances, if you plug in 0, everything zeroes out, so I'm not worried about any of those zeros. And I've got 4 times, plugging in 1 just gives me 2 plus 4 thirds. Here, 8 times, plugging in 1 gets me 8 minus 2. Okay. So let's see, 2 is 6 thirds plus 4 thirds is 10 thirds times 4. I have 40 thirds. And then 8 minus 2, 6 times 8, I have plus 48. All right. So let's see, 48 times 3 is 144 plus 40, 184 over 3. Okay. Yet again, a different value than the other two times, right? As much as you should be expected. we're picking a different path. You can even see a different set of points, a different set of z values is getting added up, even though it's the same ultimate beginning and ending point and the same function, right? Just like before. All right, now here's a step up, right? We're going to talk about a curve in all 3 dimensions, right? A space curve now over a 3-variable function, okay? So it's not like I'm going to be able to graph this, not the same way we do all the other ones. You can try to picture, different parallel surfaces, different, plugged-in surfaces of it, but you can't do the whole thing very easily. I prefer to think of it this way. The curve is going to represent a set of points in the domain, which the domain of this is the entire space, 3D space, right? I prefer to think of the line integral in this case as adding up all of the values of something being listed along the curve. So imagine walking along this curve, and every time you do, you're measuring some quantity, right? I'm not actually graphing any surfaces. I don't need to think of it like areas or volumes or anything like that. Whatever x plus y plus z is, it's some measurable quantity that I'm interested in. And then I'm following a path of x, y, z coordinates to get the different function values on, right? So maybe it's like some sort of total energy or something like that. I'm moving through space, and every time I hit a new point, I add up how much energy that point has, and then the next one, and then the next one. It's best to think of line integrals that way, okay? It's sort of a more generic way of thinking of your integral as a super summing device, right? Okay, so let's go ahead and jump in. Let's start with finding our derivative pieces so we can do our length, right? So C prime is going to be 1 and 2t squared and 2t, right? Okay, so then the magnitude of C is what we're going to eventually multiply in here, right? The length, the curve length there. Square root of 1 plus, and I'm going to put them in order, a different order than you see here. I'm going to go ahead and square this one. That's 4t squared. And then this is 4t to the 4th. If you've watched my previous videos, you already know what's coming, right? Because you've seen this curve before, right? We've talked about that curve in space before. This is the square root of 1 plus 2t squared squared. So I'm getting 1 plus 2t squared quantity for my magnitude or my length, my arc length there. Okay, so let's set up the integral then. My integral is going to be the integral from 0 to 2, because that's the interval listed. T is an element of the interval 0 to 2, right? Okay, x plus y plus z. X is t. Y is 2/3 t cubed. And z is t squared. Times ds. Well, we just calculated that to be 1 plus 2t squared dt. So now it's just a straightforward definite integral with one variable, straight from Calc 1. I just need to multiply it all out and do a bunch of power rules. Right? So let's do that. If I multiply this out, I notice that I get a t cubed here and a t cubed here. That's 2t cubed plus 2/3 t cubed. So I have a total of 8/3 t cubed. I think that's the only crossover. I got plus t, then I've got plus 4/3 t to the 5th, plus t squared, and 2t to the 4th, right? I should have 6 total multiplications. 1, 2, 3, 4, 5, 6. Yep, dt. There they are. So now I just need to to the end here. 4 is my new power, so I have 2/3 t to the 4 plus 1/2 t squared plus, let's see, 4 over 3 times 6, 18. 4 over 18 is 2 over 9 t to the 6 plus 1/3 t cubed plus 2/5 t to the 5th. Ooh, yummy. So yummy, right? Just for time's sake, of course, when I plug in 0, all of these are 0, so I'm not even worried about that piece. I'm just going to sit here and punch it up for us to save me some time and you from wasting time with things you already know how to do. So 2/3 times 2 to the 4th is 16 plus 1/2 times 4, that's 2, right? Plus 2/9 times 2 to the 6th, that's 64, plus 1/3 times 2 to the 3rd is 8, plus 2/5 times 2 to the 5th is 32. All right. Can't remember if I put parentheses or not. Okay. .23 continuous 5. Ooh, I'm getting 1906 over 45. Okay. Yes, I'm being lazy there. I apologize if my laziness offends you. I'm really just trying to save us time on things that are trivial. Okay, to really bring this into that next world where we were talking about vector calculus, then we also need to talk about doing path integrals, line integrals, inside of vector fields. Okay, so it's not just a function anymore. Now what we have is either in 2 space or in 3 space, some sort of vector field that we want to move around inside of. Okay, and this is one of the things that line integrals is really great at, and it actually even generalizes our calculus even more. Okay, a vector field, don't forget, is a function that assigns a vector to every point in some domain, right? So if I put a path inside of that vector field, then I can interact that path with the vector field by using the tangents of the path dotted with the vector field itself. And remember, dot product is all about how much does one vector contribute into the direction of the other vector that it's being dotted with, right? So as your pathway moves around in this vector field, you're constantly seeing how much the actual motion, the tangent of your movement, is being either helped or hindered or interacting with the field around you. Like imagine trying to move through a current of water, right? So a current of water is going around and you're trying to move through that current, but not necessarily with it, right? So your velocity, your motion has an interaction. And how does it interact? Your motion interacts like a dot product, with the motion of the water, right? It's kind of like that. So we'll have pathways moving through these vector fields, right? Either in 2D or in 3D, right? It can come around and have the vector fields in there. It's always going to be about the way that the tangent vectors are pointing in relationship to the vector field itself. And then the line integral comes in by doing basically a dot product at every point along the curve, and then we're going to add up all of those contributions, right? All of those dot products add up, and then you get a total amount of something, okay? So here, when you interact the vector field F with your tangent vectors with a dot product. Don't forget that what we're really doing is we're dotting the vector field f with a derivative vector, right? A vector function divided by its own length. But also, our line integrals are designed with the ds, with the length as the incremental portion. So when we do that dot product, we can really think of it as wiping out those arc length, those length vectors, those length calculations, not vectors. And so what we've really got is just the vector field dotted with the derivative vector of your path. Basically, the velocity vector itself dotted with the vector field. Okay? dt, because t is going to be whatever parameter your curve has brought out the parameterization. Okay? Sometimes this is written in shorthand as f dot dr, right? Because r is going to be your derivative piece, incremental piece of velocity. Okay? But it really means the r prime vector function, right? The derivative. And that parameterization comes from the curve itself, right? So it's over a curve, and then where do I get the r prime? From parameterizing that curve, and we call that r or c, either one. Okay? So here's an example. Let's do this one. I've got a vector field, okay? yz, xz, yx is my vector field. And I'm doing the path integral dot dr, okay? Along the curve that's a helical wrap around the z-axis, right? So I've got this thing helically wrapped around the z-axis, and I forgot to write it, but I want to go in between the values of 0 and 4 pi over 3 for t. Okay? So we'll limit our t this way. So it's just a small chunk of the helic, just helical thing going around, not even a full circle yet. Okay? All right. So my curve is this parametric, and if you will, if you prefer, right, that's basically your r. So if I'm doing this dot dr, right, then I'll think of dr like this. Is going to be -5 cosine t, -5 sine t 1 dt, right? And I'm just doing the dot product now of these two things. So I'll do x component with x component, y component with y component, z component with z component. But also, it's been parameterized, right? Y and z and x and z and y and x, those are all parameterized here. Here's the x, here's the y, here's the z from my curve, the r curve right there. So yz right there, right? The yz is really 5 cosine t times t. So that's 5t cosine t. Xz, these two multiplied, that's -5t sine t. And then yx is -25, right? Sine t times cosine t. And now I'm just going to dot that with this dr vector. Okay, so I've got my integral of 5t cosine t times -5 cosine t. So that's -25t cosine squared t. And then -5t sine t, -5 sine t. So that's plus 25t sine squared. Remember, it's dot product, so I do the multiplications and I'm just adding them all up, right? So once it comes out of a dot product, it's not a vector quantity anymore. So -25 sine t cosine t times 1, so -25 sine t cosine t, okay? dt. And that's along the curve, which we're now saying is where t is from 0 to 4 pi over 3. So now I just need to perform this integral. It's now just a definite integral in one variable, like it was before. All right, So integral, you know what? Let me make this easier on myself. I'm going to pull out a negative 25 4 pi over 3. And what that's going to do is that's going to give me some familiar pieces here, okay? I'm going to have t times cosine squared minus sine squared, like that, right? Now the t is only common to these two, which is why I didn't pull it all the way. Well, of course I couldn't pull it out of the integral sign anyway, but and then right here I'll have plus sine t cosine t dt. Okay, now those should look familiar to you, those trig pieces right there. Those are some basic trig identities from your double angle days. Right? This is just going to be negative 25 integral 0 to 4 pi over 3. I'll have t times cosine 2t and plus 1/2 sine 2t, like so. Right, it's just a couple of double angles. All right, well, the 1/2 sine 2t, that's a straightforward piece, right? I can get that one done quickly and easily. But the t times cosine 2t is an integration by parts, right? If you prefer, you can do it by chart, right? So real quick, I'm going to do this integration by parts with my UV chart. Okay, so I've got t1 and 0. I've got cosine 2t, 1/2 sine 2t, and negative 1/4 cosine 2t. And I can just do the t times the 1/2 sine t and minus 1 times negative 1/4 cosine 2t, right? There is a negative on that 1/4, and there's a negative from the by parts. Okay, so I've got negative 25 times the integration of the by parts is going to give me 1/2 t sine 2t, and plus, because of the double negative, 1/4 cosine 2t. Okay, so that's the by parts. That's this piece coming from the chart there. Now I'm doing the antiderivative of this. The 1/2 is along for the ride, and when I do the integration with the inside derivative of 2, I get another 1/2, and the integral of sine is negative cosine 2t, right? And that's going to be evaluated from 0 to 4 pi over 3. Now I hope you're seeing it. It's a really lovely thing right here. I have a plus 1/4 cosine 2t and a minus 1/4 cosine 2t. So these pieces just zero out. Lovely. When I plug in 0, right, it zeroes that piece out. That's gone. And so now all I have left is to plug 4 pi over 3 into here. So I have negative 25 times 1/2 times 4 pi over 3, because it's t, and then sine of 2 times 4 pi over 3, that would be 8 pi over 3, sine of 8 pi over 3. Well, 8 pi over 3 is bigger than a full cycle by 2 pi over 3, by 2/3 pi. So it's really the same thing as sine of 2 pi over 3, yeah? Which is in quadrant 2, so it's going to be positive with a reference angle of pi over 3, or 60. So I end up, this piece right here is just square root of 3 over 2. Sine of 60, basically, sine of 120. Okay, so over 2, wipe out with the 4, and I am left with negative 25 pi square root of 3 all over 3. So a path integral inside of a vector field, right? Since I'm dotting them, they do actually just give me numerical contributions at each point. They're dotting at every point. So before we move on, I want to discuss how the orientation of your parameterization really makes a difference in the vector field line integrals, okay? We have our line integral of this guy that we just did, okay? And it was this helix that started on the bottom and it spiraled upwards, right? So my tangent vectors were constantly going upward like this and spiraling around. Take the same vector field, okay? And then the same curve, but I'm going to parameterize it a different way. This is the same curve as this one on those values of t and these values of t, okay? Let me show you what I mean. If you plug in, say, 2 pi, right? 2 pi minus 2 pi is 0, right? And 5 times cosine of 2 pi is going to be 5. And then 5 times sine of 2 pi is going to be 0. So I have 0, 5, 0, which, notice if you plug in 0 over here, right? I get 0, 5, 0 as the beginning point, whereas over here it's the ending point, okay? Just an example. Also plug in 2 pi over 3. You'll see that what you get is the same thing as if I plug the end point in over here. So this is what I've done. They're winding at the same rate. You can see the 5 sine and 5 cosine just like that one. But it's a minus t now instead of a plus t. So it's the same spiral, okay? But that one spirals upward. This one starts at the top and spirals down the exact same curve. They're the exact same path, not just the same beginning and ending points. These two follow the exact same path. However, the parameterization is reversed in orientation. So whereas the tangent vectors on this one were pointing in the upward direction, like increasing the spiral, all of the tangent vectors on this guy are going to be going down the spiral. They will be 100% anti-parallel, right? So if those vectors are pointing this way, all of these vectors will be the same size, but pointing the other way at every point of the same path, okay? So let's do this integral right here so that you can see that what happens is all of the dot products are the opposite sign. I'm going to get the same value, but the opposite sign answer, okay? And that's going to be true for all of your path integrals inside of a vector field. So let's get my dr, right? I've got 5 cosine here, negative 5 sine, and then negative 1 this time, right? So you can see that the tangent vectors are practically the same, right? But just a little bit different, right? We've got the opposite directions is going down, and then the x direction is opposite as well. So now we're going to do the dot product, right, from here to here. And it's basically the same setup as over there. The yz has been replaced, the xz has been replaced, the yx has been replaced. So we just need to write down real quick to remind us. Y times z is going to be 5 2 pi minus t times cosine. X times z is going to be 5 2 pi minus t times sine. And yx is going to be the same over there as it was, but 25 is positive this time. Sine t cosine t, right? Okay. So we're going to dot those with the dr. And then we're going to have our integrand. So integral from 2 pi over 3 to 2 pi. And then I've got 5 cosine times 5, 2 pi minus t cosine. So that's 25, 2 pi minus t cosine squared plus, I've got a minus this time, so minus 25, 2 pi minus t sine squared. And then negative 1 times this one, I've got a minus 25 sine t cosine t. And then, of course, the dr technically should have a dt here, right? dt. Okay. All right. So then I, of course, can factor out that 25 again. And you'll notice that I have the 2 pi minus t shared here, right? And what I've really got is cosine squared minus sine squared again. Okay, so integral 2 pi over 3 to 2 pi. And I'm going to have 2 pi minus t times cosine 2t, right? Because that's the cosine squared minus the sine squared identity again. Okay, minus. And then that I pulled the 25 out, but then that's the same identity as before, right? 1/2 sine 2t dt, like so. Okay, then what? All right, well, I'm going to have to do my integration again, right? Again, this is the same straightforward integration as it was last time, right? It's the same straightforward integration. And this one is also a by parts integration because it's t times cosine 2t. Okay, so let's go ahead and do our little chart method again like we did last time for the by parts part of it. I'll do my little UV chart. I have 2 pi minus t for one part. I have cosine 2t for the other part. Derivative is -1 and then 0. Integral is going to be 1/2 sine 2t. Integral again is going to be -1/4 cosine 2t. And then I'll have to do my diagonals, right? This one with that one, and then minus this one with that one. Okay, so let's write that out. I have 25 times 2 pi minus t times 1/2. Let me squeeze that in. And I've got sine 2t. I've got minus 1/4 cosine 2t. Okay, that's the by parts. Just like before, when I do this separate integral right here, I'm going to get a plus 1/4 cosine 2t. Like before, these guys are gone. And it's 2 pi over 3 to 2 pi. Okay. Well, what happens when I plug in the 2 pi? 2 pi minus 2 pi is 0. And that's the only piece left. So 2 pi is no more good. Don't forget, I'm doing top minus bottom. So I'm getting a -25 times 1/2. 2 pi minus 2 pi over 3. And then I'm going to get a sine of 2 times 2 pi over 3, which is 4 pi over 3. Okay. So 2 pi minus 2 pi over 3 gives me 4 pi over 3. And sine of 4 pi over 3 is negative square root of 3 over 2, because it still has that same pi over 3 reference, but it's in quadrant 3. Okay, look, double negative. And then the 2 and the 2, 4, cancel out the 4 like before. I end up with a 25 pi square root of 3 over 2. Again, not a coincidence that it's the same numbers but opposite sign, because this curve is the exact same curve as this one. They map out the same points, but the orientation is reversed on this one. So they follow the exact same path, but they do it in the exact opposite order. So all of the tangents are 100% opposite here, right? They're going in the other direction at the different points, okay? So keep that in mind when you're doing a line integral in a vector field. The orientation that you pick does actually matter for the answer, okay? So here's that vector field in 3D space. let it, look around it for a second there so you can kind of get a feel for what it looks like, because it's pretty densely packed in there. Starting to get a feel for it. You can see the way it feels like it wants to swirl in some places. Right, you can see right here it wants to flow kind of downward and then inward right there. All right, now we're also interested in the path. There it is. So that's the forward one. This path, whenever I hit the thing to go, you can see the path that it takes to go around the helix. Now what you need to be paying attention to is what happens to the tangent vector, right? It's going through this big thick of vectors here, and as I'm doing my line integral, I'm adding up the dot product of all those pieces with the tangent vector right there. So as it goes through, it goes through this way. Okay, so now, real quick, let's try to reparameter the way that the second way we did it there. It was we had a positive on the 5, and then with the t there we had 2 pi minus, and then the t went from 2 pi over 3 to 2 pi. Okay. So what you need to notice is that the curve is the same there, right? It hasn't changed at all. But as I get t over to it, you'll notice the direction of the tangent vector. Look really closely, because that was just like the thing we were doing earlier, right? Right there, you can see the tangent vector is pointing the other way now. It's completely the other way. And if I let t go, this is the orientation of the path now. It's completely the same curve, just parameterized so that it flows in the opposite direction, which is going to give you the same result in the integral, but just with an opposite sign since it's a vector field. One major application of line integrals, path integrals, is work in physics. Work being the amount of energy expelled in actual motion, not necessarily to be confused with energy just expelled. For example, if I push on this wall, I'm expelling energy, but nothing's moving, so no work is being done. Versus if I push a buggy, right, into Walmart, I'm actually performing work because my force is causing the buggy to move, right, a certain amount of distance. Now, of course, depending on the angle to which I push the buggy, either some or all of my force is going into the motion, which is why it would be a dot product, right? The force that you're exerting going along with the tangent vector of the motion, right, or the dr of the motion. If you're pushing a buggy like this, not all of your force is going into that, by the way, right? Your tangent vector's here, right? It's not in the same direction as your force vector. Some of your force is getting wasted in the downward direction. If you had something heavy, you'd get down and you'd have to push it, get down into the field of it. So it's like your brain already understands dot products and vector fields like that a little bit from experience. Anyway, the work is going to be this same line integral that we've already been talking about. Okay, so here's an example. Let's say we're in some sort of electric field, and let's say that field is devised by this particular 2D representation, 2x over y and negative x squared over y squared. Okay? And let's say I want to move in a path from the point 0, -5 to the point 3, 4. Okay? I'm going to do it two different ways. First one, in a straight line, right? So I'm going to go in a straight line from this point to that point, and this is the parametric breakdown of that, right? So if I plug in 0, right, I'll get 0 and -5. If I plug in 1, I'll get 3 and 4, okay? So it's a straight line, and t is going to vary between 0 and 1 there. All right, so that means that I'm going to be doing the integral along the curve C1 of E dot dr, like so. Okay, so then that's going to be the integral from 0 to 1. My E field in terms of t, right, that's going to be 6t over y, which is -5 plus 9t, comma, x squared, so -9t squared over y squared, which is going to be the -5 plus 9t all quantity squared. Okay? And I'm going to dot that with dr. So let's figure out what dr is real quick. dr is going to be 3 and 9, right? dt. Cool. So I've got 3, 9 dt. And I'm just dotting these now, right? So I've got 3 times the 6t, and I've got 9 times the -9t squared, and the denominators are still there, and I'm just going to be adding this up, right? So an integral from 0 to 1, and I've got 18t over -5. I'm just going to write it as 9t minus 5 to make it easier. 9t minus 5 minus 81t squared over 9t minus 5 squared dt. Let's try the common denominator route. And I'm going to factor a 9t out as well. So 9t times, the common denominator is going to give me another 9t minus 5 up here, times 2. 9t minus 5 minus 9t, because 9t times 9t gives me the 81t squared, and all of that is over the common denominator of this squared. Notice this is giving me 18t minus 10 t minus 5 squared dt. So right here, if I distribute the 9t, I want you to notice that that's 81t squared minus 90t, which is the same two terms you get in the front if you FOIL this out. 81t squared minus 90t plus 25. So in the top right here, if I do a plus 25 and a minus 25, I can simplify this thing greatly into this integral here from 0 to 1. This portion over itself is just 1. And then I'll have minus 25 over the original denominator, but I'll leave it in factored form. 9t minus 5 squared dt. From here, straightforward integral. That's just going to be t plus, because it'll be the negative 1 power divided by the new power, 25 over 9, because of the inside derivative of 9, and times 1 over 9t minus 5. And that's going to be evaluated from 0 to 1. Okay? So when I plug in the 1, I'm going to get 1 plus 25 ninths times 1/4. So that's 25 over 36 minus 0, and then minus negative 5 ninths. And when you combine those up, you get 9/4. Okay? So yeah, a little bit yucky right there in the middle, especially with a lot of the factoring pieces. Still mostly doable though. Okay? Same thing, but let's go with this other path. Okay? So I've got C2 that's moving in this field, and it's going to move in a circular path, right? Cosine and sine, that makes a circular path. But we need to talk about where it begins and where it ends, right? So in that circular path, I'm going from 0, -5, which is down here, all the way up to 3, 4, which is up here. Before we went straight between them, now I'm doing like a circular type of path up to it like this, right? Now, of course, the t value, when it's pointing down like this, right, it's like an angle. That means it's going to be negative pi over 2 is where t would start. And then, of course, it's going to have to rotate from here to here, up to where the 3/4 is, to whatever angle the 3/4 causes. That's going to be the arctangent of 4/3. Right? That's how we convert from rectangular to polar, remember? Because I've got the point over 3 up 4. So the angle that it's at is going to be the arctangent of the opposite side over the adjacent side, right? Arctangent of 4/3. Okay, so I need to have my dr. In this case, that's going to be -5 times sine and 5 cosine, right? That's my dr. And I'm going to be doing the integral of the E field dot dr. Okay, so integral from -pi over 2, and I'm going to call this thing a letter for now, right? This letter right here, I'm just going to call it theta, because we're not using it anywhere else, and I don't feel like writing arctangent a whole bunch. Okay, save some space. So then my E field is 2x over y. So 2 times x is 10 cosine over y, which is 5 sine. And then negative x squared over y squared. So negative 25 cosine squared over 25 sine squared. And I'm going to be dotting it with this vector here, the -5 sine and 5 cosine dt. Forgot my dt here. Right? All right, so we're dotting that. This one times this one. So integral from -pi over 2 to theta. And I'm going to have a -10 sine over sine, so it's just -10 cosine t. Yay. And then negative again, these 25s wipe out. -5, I'm going to have cosine cubed t over sine squared t, like that. Okay. Well, let's see what we can do. Oh, dt. Right. Let's see what we can do to simplify this a bit. First and foremost, I can definitely take a -5 out. That will help a bunch. Get those numbers out of the way. I'll have 2 cosine t right there. And let's see. Let's go ahead and split a piece of this right here. That's going to give me 1 minus sine squared times cosine divided by sine squared t, right? Alrighty, so then I can distribute the cosine t and the sine squared there. Okay, yeah, that's going to be nice. So integral from -pi/2 to theta. And, oh, forgot my -5. Right, got my -5 there. 2 cosine. I'm going to have plus cosine t over sine squared, because that's just the cosine, and then under this. And then, of course, minus cosine will multiply here, but sine squared over sine squared is just 1, so minus cosine t, right? Let's make that a little bit shorter for ourselves. It's just minus cosine t, so then I'm just going to have one of those here, dt. All right, so -5 integral -pi/2 to theta. I've got cosine t plus, now there's 2 signs in the denominator here, so it's cosine over sine times 1 over sine. Cosine over sine is cotangent of t times 1 over sine is cosecant of t dt. Both of those are pretty straightforward antiderivatives, right? I can do the antiderivative of cosine, and then cosecant cotangent is the derivative of cosecant, right? Well, negative, of course. Okay, so I've got -5 sine t minus cosecant t. And that's evaluated from -pi/2 to that value of theta we had up there, the inverse tangent of 4/3. Okay? To make that a little bit easier for the plugging in part, let's draw a triangle for that value of theta there, right? Technically, it should be on the x-axis like this, right? Such that the 3 is on this side, the 4 is on this side, and this is our angle. Of course, that makes the hypotenuse 5, right? So if I plug this theta into sine t, I'm going to get 4/5, which of course then makes the cosecant 5/4. Okay, so let's start there. I've got -5 times 4/5 minus 5/4 minus sine of -pi/2 is -1 minus cosecant at -pi/2 is also -1. So +1 with a double negative. And this piece actually goes to 0. So what I'm left with is 4/5 minus 5/4, which is what, 16 minus 25 over 20. Which of course is -9/20. Double negative, and then the 5 over the 20 is going to give me 9/4. All right, so I'm hoping you're noticing that we came out with the same answer this time. I did say that not always could this happen, but there are some cases where it could. There are certain types of vector fields where the path that you use doesn't matter. They had the same beginning and ending points in this case, and this is one of those special fields where no matter which way you integrate it, you come out with a same answer. That's something to keep in mind when comparing, some messier integrals versus some slightly less messy integrals. And then also later on in a couple of sections, there's a way we can take all of this work and shrink it up into almost nothing, depending on the type of field you have. So let's look real quick at the vector field there. This is the vector field 2x over y, negative x squared over y squared. I have it set up pretty well, as you can tell. Let's see. That might be a little too thick. Let's go back one again. Okay, yeah. So you can see the direction of the swirling there of the vectors, kind of fighting against each other from left to right, but still. And here's our curve that we're integrating over. The one thing that you'll be able to notice is that as this thing goes all the way across, the tangent vector pretty much stays the same. Well, not pretty much, it does. So it's baffling a little bit that I can just sit here and add the same number over and over and over again. Well, number same for itself anyway. What does change is the other vectors around it. Okay, now let's take a look at the other parameterization of it, which would be for me to change these functions here into 5 cosine x and 5 sin x. And then we'll want to change the curve such that it goes from negative pi over 2 to arctangent 4 Okay, so turn off the vector field for a second so that you can see where we're at here. Oh, I gotta put this thing right here. We'll fix that. Okay. There we go, that's better. Okay. So let's turn off the vector field for just a second so that you can see the curve that we're going to be using now. Notice it's the same 2 points, right? The 0, -5 and the 34. And I'll be going in the direction from the bottom to the top here with that particular parameterization. So here's the vector field, and let's see, let's back it off a bit on the vector field if we can, It goes right through that thick point right there. The vectors get really big because of the division by the thing there. You can see the little bitty vectors there, and we'll get it going. But so anyway, my vector's going this way. As you can see, as it gets into where it is right now, it's starting to fight against those vectors. And there you have it. Okay, that's what's actually happening there. One last example so that I can show you yet another way that some line integrals can be performed. Let's start with doing this one the way we've been doing it, and then I'll show you the alternate way that can come up in these other situations. All right, so I have this vector field, right, in 2D, and I'm going to go along this hyperbolic curve, x times y equals 6, right? And I'm going to go from 2, 3 to 6, 1, okay? But in this first part, I'm going to use the parameterization of this curve where r is equal to 2 secant and 3 cosine t, right? You would notice that if you multiply x and y, x times y, 2 times 3 is 6. Secant times cosine, they're reciprocals, they give you 1. So you do always get 6 when you multiply these two. This is a very good parameterization of that curve, right? So if I'm going from 2, 3 to 6, 1, then I just need to write down what values of t cause that to happen. Okay, so notice I just need the secant and the cosine to be 1 for the 2, 3. That's easy enough. Right here, I'll let t be 0, because that's where cosine is 1 and secant's just the reciprocal. Okay, now for this one, since this is going to be 1, I need the cosine to be 1/3, right? So this is going to be when I have the inverse cosine of 1/3. Not exactly a winning angle, not one of our favorites, but it can work. Okay, so to set up my line integral, I'm going to do b dot dr, right? So first of all, b, after I set it up, is just y over x, right? So that's 3 cosine over 2 secant, and then negative x squared. So that'll be negative 4 secant squared t, right? That'll be my vector field. And then I need my dr, right? So the derivative of secant is secant tangent. So secant t, tangent t. And of course the derivative of cosine is negative sine. Okay? So I'm doing the integral along the path of b dot dr, right? So I've got 3 cosine t over 2 secant t times 2 secant t tangent t. Well, notice the 2 secants are going to immediately wipe out when you multiply those, and I'm left with 3 cosine times tangent. But what's cosine times tangent? Come on. That's just, whoops, forgot my integral sign. Integral from 0 to, I'm going to do like I did last time. I'm going to call this theta. Right? Okay. Again, what cosine times tangent, right? That's just sine. Right? Cosine times tangent is just sine. Okay. Negative times negative, 4 times 3, I'm going to get a plus 12. Secant squared times sine. Let's see. Secant squared times sine. Well, that's pretty easy. Instead of secant squared, I could just write this as 1 over cosine. And what's sine over cosine? Always forgetting that dt, aren't I? Sine over cosine is just tangent, right? So I've got secant tangent here. Both of these pretty straightforward antiderivatives. I'm going to have negative 3 cosine t plus 12 secant t, right? Antiderivative of secant tangent is just secant. And it's going from 0, I'll go ahead and write it out this time, to the inverse cosine of 1/3. Well, look at what happens. I'm plugging inverse cosine of 1/3 into cosine, right? What are you going to get? 1/3. Okay, so I'm starting out with a -3 times 1/3. Plus, if I do the inverse cosine of 1/3, secant's just the reciprocal of the cosine value, and I'm saying the cosine value is 1/3. So reciprocate that, and I've got times 3. Okay, now plug in 0, right? Cosine of 0 is 1, so that's minus -3. And secant of 0 is also 1, so that's minus 12. Okay, so what have we got? We got -1 plus 36 plus 3 minus 12. That's 39 minus 13, which is 26. Okay? All right, so just like before, right? We just did b dot dr over the curve. Okay, so here's another thing that can come up here. If you happen to have a vector field and you're dotting it with dr, don't forget that dr is just made up of the composite pieces of dx and dy in vector form, right? This is a vector, okay? And it's basically dx dy in vector form. So if I'm dotting it, I'm getting m dx and n dy from the dot product. Okay, so in this case, m is y over x, and n is -x squared. And then I'm going to be doing the curve xy equals 6. So let's look at this again. If I have the integral over our curve of b dot dr, that means what I have is the integral over our curve of y over x dx plus -x squared dy. And then we can clean this up a little bit because our curve C is given by this relationship between x and y, right? Okay, so my relationship between x and y is xy equals 6, and I have the points 2, 3 to 6, 1, right? From 2, 3 to 6, 1, like that. All right, so this is really two separate integrals, right? Because one's a dx and one's a dy. So for dx, that goes from 2 to 6 in my points, so 2 to 6. And y is equal to 6 over x. So I have 6 over x times 1 over x dx. Okay, minus, because of the negative here, the integral for dy goes from 3 to 1. From 3 to 1. And then it's x squared. Well, okay. X is equal to 6 over y. So 6 over y squared dy. Right? Right here, instead of times 1 over x, I could have just said 6 over x squared, right? And right here, I can just say 36 over y squared. Absolutely. Okay, so some pretty straightforward antiderivatives here. This is just going to be x to the -2 going up to x to the -1. So I'm going to have -6 times 1 over x, evaluated from 2 to 6, minus, of course, then that'll become plus because of the new power, 36 times 1 over y, evaluated from 3 to 1. All right. So let's see, I've got -6 times 1 over 6 minus 1 over 2 plus 36 times 1 over 1, which is 1, minus 1 over 3. Okay? Well, if I distribute this 6, that'll make that a lot easier. That's just going to be negative 1 plus 3, and then 36 minus 12. Those numbers look familiar, don't they? It equals 26. And again, this one's not even a trick of, parameterization or anything else like that. We physically did the same integral, just a different way. It's the same path, the same orientation. I just didn't bother parameterizing the curve. I simply used the curve as a relationship to turn the x's and y's in with each other. Okay? Well, I hope this helps you understand line integrals on your endeavor for vector calculus. So here's a quick look at that one that we just calculated the two different ways. Let's get it to where we can see it pretty well. That's not too bad. The size is kind of large there, but let's see what happens when we get really big, right? You can see them start to separate out there. Okay, well, let's leave it where you can see it a good bit, the density of it, right? You can see a lot of the vector goes this way, like this. So at first, my vector starts out kind of in league with them there. And then, as it increases, it starts to turn away more perpendicular. So in this line integral, the first part that we're adding up there has the majority of the numbers that we're adding up at first there, where the vector wants to be in line with them.